All right, on question 1, we wanted to, for each of the following balanced equations, calculate how many grams of every product would be produced by the completely reaction of 15.0 grams of the reactant in bold. All right, so on this first one, we're going to take 15 grams of boron. I'll start by turning that into moles. 1 mole of boron is 10.31 grams. Now, that I'm getting right off the periodic table. I don't have that showing up on the screen, but that just came right off the periodic table. And then 2 borons makes, I'll do the boron trichloride first, make 2 boron trichlorides. Then 1 mole of boron trichloride. Let's see. I'll write the molecular weight over here. So I have 1 boron at 10.31 grams and 3 chlorines at 35.45 grams. And that gives me 117.16 grams. Now, before I do the calculation, I'm going to go ahead and write down the second calculation. So we're going to take also that same 15 grams of boron and convert it into moles the exact same way. But now I'm going to compare it to make the other product. So 2 borons for every 3 hydrogens. And then 1 mole of H2 is 2.016 grams. All right, so our calculator, 15 divided by 10.31 times 2 divided by 2 times 117.16 is 170 grams. And 15 divided by 10.31 times 3 divided by 2 times 2.016. And we get 4.40. All right, next one, I got copper, and it's also going to be 15 grams of copper. Periodic table, you see that 1 copper is 63.55 grams. The first one, I'm going to take those 6 coppers and make 2 copper oxides. It's O minus 2, so this would be copper 1 oxide. And then 1 mole of copper oxide, 1 times 63.55, well, 2 times. And then oxygen is 1 times 16. Cu2O is 143.1 grams. And then 15 grams of copper, 1 mole of copper to 63.55 grams. Now we're going to go those 6 coppers into 1 Cu2S, copper 1 sulfides. And 1 mole of copper 1 sulfide is 159.16. Similar calculation. Just adding about double the mass because sulfur is 32.06 grams. Okay, so we have 15 divided by 63.55 times 2 divided by 6 times 143.1. We get 11.3 grams. And our other one 115 divided by 63.55 times 1 divided by 6 times 159.16. And we get 6.27 grams. All right, so what is next? All right, on 2, going to do something very similar, but I gave you an unbalanced equation. So the very first thing we're going to need to do is actually balance that equation. All right. And so coppers are fine, 3 chlorines, so 3 silver chlorides gives us 3 silvers, so 3 silver nitrates, and that fixes the nitrates. So we just need the 3s. All right, and I gave you 25 grams of copper chloride, copper 3 chloride. So copper is 63.55 grams, and chlorine is 35.45 grams. Those together give us, ooh, I got that fraction upside down, don't I? 1 mole is on top. I want the masses to cancel. And this is 169 point, looks like 90. And then this 1 copper chloride could turn into 3 silver chlorides. And AgCl, I'm going to change this color just so it doesn't clash. So there is 1 silver, and a silver weighs 107.9, and the chlorine is still 35.45. So this is 143.3. Should change that so it's the same color. Okay, and our second calculation, 25.0 grams of the copper 3 chloride. And now we have 1 copper into copper nitrate. This is a lot more on this last one, so got the copper. Have nitrogen, but there is 3 of those. And 9 oxygens. So the copper nitrate is 249.58 grams. All right. Have 25 divided by 169.9 times 3 times 143.32. And we get 63.3. Very similar calculation. 25 divided by 169.9 and then times 249.58, and we get 36.7. Okay. Excuse me. All right. Interesting dilemma. I don't know where I got this problem from, but that stuff doesn't exist. I don't think copper forms a positive 3 ion. All right. Oh, next one's nice. I don't have to do 2 times because I have 25 grams of aluminum and we only have one product. However, this problem is not balanced, and we do see for 1-to-1 aluminum, but there's no way I'm going to get 3 there, so I need to come in here and say 2 of these to every 3 of those to balance out the bromines. Therefore, it's 2 aluminums. All right. Now, 1 mole of aluminum. Get onto the periodic table, we see that aluminum has a mass of 26.98 grams. And our balance equation says there's 2 aluminums for every 2 aluminum bromides. And then 1 mole of aluminum bromide. We're going to get that from, so we have that 1 aluminum at 26.98 grams. And bromine, 3 of them, those are 79.90. Giving us a total of 266.68 grams. So 25 divided by 26.98 times 2 divided by 2 times 266.68, and we get that 247 grams. All right. And the last on this page, that CH3CH2OH, that is ethanol. Don't necessarily need that for this problem. Need to know the name that is. But I figured that'd be interesting to add in there. That is the stuff we find in up to 10% in your gas tank. Very small percent in your booze. So ethanol. And that is 1,2 carbons. 1, 2, 3, 4, 5, 6 hydrogens. And 1 oxygen. Giving us a molecular weight of 46.07 grams per mole. All right. Need to balance our equation. We have 2 carbons, so I come in here and say 2 here. 6 hydrogens, so I'd say 3 there. But I have an odd number of oxygens, so to fix that, we're going to double everything we just did. So I have a 2 in front of this, giving us 4 carbon dioxides and 6 waters. Grand total of 8, 14. I need 7 O2s. Yeah. All right. So our balance equation, we have for every 2 ethanols, we would produce 4 carbon dioxides. And can use those same numbers to get the molecular weight of carbon dioxide at 44.01 grams. And then we'll do the same thing, but this time with the water. So instead of 2 ethanols for every 4 carbon dioxides, it's 2 for every 6 waters. And trusty dusty calculator. 25 divided by 46.07 times 4 divided by 2 times 44.01. We get that should be about 47.8 grams. And 25 divided by 46.07 times 6 divided by 2 times 18.01. And we get 29.3. So 29 grams of water, about 50 grams of carbon dioxide. All right, page 3. Another set of unbalanced equations. This time I'm giving you 10 grams of all the reactants. We got to figure out which one's in excess. And then once we know how much whichever one's in, which one's limiting, we'll be able to figure out how much left over, how much of the unreacted reagent is left over. All right, so going to do one calculation with the 10 grams, and we're going to assume we're going to just start with silicon because it's the first thing there. We're going to figure out how much carbon monoxide would be needed. So from the periodic table, I see that 1 mole of silicon happens to weigh 28.09 grams. And we need to balance this equation. That one was kind of easy to balance. So for every silicon, you would need 2 carbon monoxides. And carbon monoxide, 12.01 plus 16, that is a mere, 28.01 grams. All right, so to use up all 10 of our grams of silicon, so 10 divided by 28.09 times 2 times 28.01. To use up all 10 grams, we would need 19.9 grams of carbon monoxide. We don't have that, we have only 10 grams. So because of this first line, we know that, carbon monoxide is limiting. All right, but unfortunately, this number doesn't help us to know how much is in excess. So to figure out how much is in excess, we got to do the second calculation, this time using 10 grams of our limiting reagent, the carbon monoxide. There are 2 carbon monoxides for every 1 silicon, and then 1 mole of silicon is 28.09 grams. All right, so 10 divided by 28.01 divided by 2 times 28.09. We see that this requires a mere 5.01 grams. Therefore, the amount remaining is 4.99 grams of silicon remains. And I did that from 10 minus 5.01. All right. On this next one, I'm going to do things a little bit different to show you how this could have happened. I know if I start with the 10 grams of sodium carbonate, I'm going to get the same type of thing where I have to do the calculation twice. But I'm going to do it with 10 grams of the HC2H3O2, which happens to be vinegar. And we're doing the same type of thing as we did up here, so we're converting it to moles. And acetic acid happens to have a molecular weight of It's at 60.08 grams. All right, and I want to relate it to these two. But remember, this was not a balanced equation. So I have two sodiums. So two sodiums. That gives me two of these acetates. So I'm come back here and put a 2 in front of that. Those two H's end up with that CO3, giving us the CO2 and a water. All right, so that's balanced. So I have two acetic acids for every one sodium carbonate. And molecular weight of sodium carbonate is 105.99. All right, so did the same type of thing. We just chose the 10 grams of one of our two components and plugged it in. This is going to tell us which is the limiting reagent. So 10 divided by 60.08 times 1 divided by 2 times 105.99. All right, to use up all 10 grams, we would need 8 or so, 8.82 grams. All right, we have that. So since we have that, we know that the HC2H3O2 is limiting. And we're just going to do 10 minus this and see that the amount of sodium carbonate left over is about 1.18 grams. So it just so happened by doing it that way, we only had to do the one calculation because we got lucky, I guess you could say, with our choice of the vinegar being used up first. All right, next one, and I will have another video for this one. This is a little bit more complex being that it has 3 reagents. But what we're going to do is similar to what we did with A, and I'm just going to grab the 10 grams, and I'm first going to grab the Na2B4O7. Excuse me. All right, the sodium tetraborate, the B4O7 is, I'll put that over here, B4O7, and it's a 2 minus. That is called tetraborate. Don't need to necessarily know that, but you're going to hear me say sodium tetraborate a lot. I figured tell you where that came from. All right, now the molecular weight of the sodium tetraborate, happens to be 201.22 grams. All right, need to balance this equation. And I'm going to start with the sodiums and see that I need to get oops, that's a weird looking 3, a 3 to 2. So we get 6 total. And I am going to look at just the boron. Something to help us out often, we see that the polyatomic ions stay intact. So you would have counted the tetraborate as one thing. We're going to do that with the phosphate. The PO4 stays intact on both sides. But you see that the tetraborate's not found in the products. It gets turned into this just borate, BO3. So the boron falls apart. So we're gonna just follow the borons themselves. So 3 times 4 is 12 bromines. Therefore, we'd need 12 H3BO3s. All right. Now, normally I'd skip hydrogen because it's found in both situations, but we're not going to skip the phosphate, the PO4 part. Since it stays intact over here, we're going to assume that every bit of that phosphate is this phosphate. So since there were 2 phosphates in this sodium phosphate, we need to have 2 H3PO4s. All right, to do the rest, we're going to try just do either the hydrogens or the oxygens. Since the oxygens are nice whole numbers, I'm going to try to follow the oxygens, and then we'll do the hydrogens. All right, now I'm going to skip the oxygens that are in the phosphates, because if the phosphate stays intact, we can actually safely say they stayed together. So we can ignore those 4 or 8 oxygens. So we're going to focus on just the 7, giving us 21. So right now I have 21 oxygens as reactants. And on products, I have just 2 times, or 12 times 3, 36 oxygens. Difference there, this would need to be 15. All right, to double check that, what we would do now is just actually total up our hydrogens. Right now I have 12 times 3, so 36 hydrogens. And I have 30 plus 2 times 3. There's our 36. So that is balanced. So 3, 2, 15, 12, and 2. All right, so our sodium tetraborate, we convert it into moles, and our balance equation says there are 3 sodium tetraborates for every either 2 H3PO4s or 15 waters. I'm going to do just the H3PO4 first of all. So when this calculation is done, I will know the limiting reagent between just the first 2. And H3PO4 happens to weigh 97.99 grams. All right, now, before I'd actually go ahead and write something down before I do the calculation, I need to do this calculation because I need to know between these 2 which is the limiting. All right, so 10 divided by 201, 201.22 times 2 divided by 3 times 97.99. And we get that this needs a mere 3.25 grams. All right, since it only needs 3 grams of the H3PO4, we know that between these 2, the N2B4O7 is limiting. So now I want to figure out between the sodium tetraborate and the water, which one's limiting. So I'm going to do the exact same calculation again. But I'm going to use, that's the next one. This one's the same thing. Here I'm going to say for every 3 of the sodium tetraborates, we need 15 waters. And 1 mole of water happens to weigh 18.016 grams. All right, this looks big because at 15. But 10 divided by 201.22 times 15 divided by 3 times 18.016 gives us that this is a mere 4.48. All right, both of these helped out quite a bit because what this tells us is the sodium tetraborate is limiting because all 10 grams would be used up, and yet we've only used 3.25 grams of water, which would mean that there is 6.75 grams of the H3PO4 remaining. And there is 5.52 grams of water remaining. Remaining. Running out of space, so I'm dropping letters. Okay, now that one is kind of complex. I'm going to do another video where we can kind of use the molecular weights and these ratios to figure out roughly how fast they go through. They'll help us predict the limiting reagent based on just the moles, but that's another video. All right, question 4. Turns out this is probably the easiest one of the problems simply because we only have one calculation to do. So it wants us to get the maximum mass of copper produced from this. And I just have 16 grams of zinc. So I'm going to look on the periodic table and see that 1 mole of zinc is 65.38 grams. And then it wants me to figure out the most copper that's produced. So I'm looking at the ratio of copper to zinc. Need to reverse that. Zinc's on the bottom. All right, but I have an unbalanced equation right now. So the Cu2SO4 tells me I need to have 3 of these to get the sulfates and 2 of those to get the copper. And that gives me 3 zincs. So it gives me a ratio of 3 zincs to every 2 coppers. And then 1 mole of copper happens to weigh 63.55 grams. So trusty dusty calculator here. 17 divided by 65.38 times 2 divided by 3 times 63.55. And I get 11.0 grams of copper. Okay, the 11.0 grams of copper is the maximum possible. So that's the theoretical yield, but it wants to know what percent yield is. So to get the percent yield, we see that we only made 10.5 grams. And we're just going to take that and divide it by the 11 we just found. So actual over theoretical. And we're just going to turn that into percent. So 95.3%. All right. Thank you very much.